Okay, next we have energy of continuous charge distribution. We already know that the work done in bringing endpoint charges somewhere in a space, then the energy stored in assembling those endpoint charges is given by this relation. W is equal to 1 over 2 sum over I started from 1 up to n Qi V of Rj. This is, let us say, equation 1. Now this work done can be stored in the form of potential energy. Now this is the expression for bringing endpoint charges or assembling endpoint charges. They are located in infinity and bringing those endpoint charges to a specific region. Suppose these endpoint charges. But if the number is uncountable, like we bring a large number of charges such that the assembly looks like a continuous charge distribution. It looks like this. So here we have charges, here we have charges, here we have charges. So it looks like a continuous charge distribution. Then in that case, we will replace this integral summation by an integral sign. So we have the total work done, which will be equal to 1 over 2, and this summation will be replaced by the integral. Instead of q, we will replace dq, and instead of potential, we will replace v. Now this is for the work done. In assembling a large number of charges. Which looks like a continuous charge distribution. Suppose the charges we assembled to a region. That region has a volume V and charge density rho, volume charge density rho, which is given by charge per unit volume. I represent this volume by this tau, d tau. So from this we can write dq is equal to rho into d tau. So if I put in this in above expression, then the work done will be equal to 1 over 2 integral of rho v into d tau. If this is equation 1, this will be equation number 2. This will, I call it equation number 3, and this is equation number 4. Now the differential form of Gauss law is del dot E is equal to rho over epsilon naught. I can write from here rho is equal to epsilon naught times del dot E. This is equation 5. Using 5 and equation 4, we have W is equal to epsilon naught over 2 integral of del dot E, and we have V into d tau. This is, let's say, equation number 6. Now we know that del dot V into E can be expressed as, this is just a differential derivative operator. So operate this operator on this quantity, we have del V dot E plus V into del dot E. Because E is a vector quantity, V is a scalar, so scalar will be multiplied like normal scalar number with this quantity. So the dot product is always between vectors. So here del into V, this is a vector, so dot E. Now this is a scalar, so there will be no dot product here. So the dot product will be between del and E. From this we can write V into del dot E is equal to, this term is del dot VE, and I bring this term to this side, so minus del V dot E. I can write it as del dot E into V. This term can be written like this, is equal to del dot V into E minus del V dot E. This is, let's say, equation number 7. So using equation 7 and 6, we have W is equal to epsilon naught over 2 into, we have now two integrals, so instead of this term I will put these two terms, so integral will be separately on these two. So the first integral is del dot VE into d tau, and the second integral is minus del V dot E into d tau. This is the final expression now. We have to simplify this expression first. Now apply Gauss divergence theorem to this first terms here. This is the volume integral, and the volume integral of divergence of some vector quantity can be replaced by surface integral according to Gauss's theorem. This is the surface integral now, this is the volume integral. This volume integral will replace by the surface integral times VE dot dA minus, this term is written as it is, del V dot E into d tau. So the divergence theorem is volume integral of del dot some vector quantity A is equal to into d tau, yes, is equal to, this is the volume integral, surface integral of that quantity dot A. This is the volume integral. So divergence theorem. So I applied this divergence theorem to this one, I got this relation. Now we know that E is equal to, electric field is equal to minus negative gradient of potential, del V is equal to minus E. So replace this term here by this minus E. So we have work done is equal to epsilon naught over 2 integral of, we have this bracket, integral of VE dot dA. Now one minus sign is there, one minus sign is this one, so it will become plus integral of E dot E, so it will become E square into d tau. So our final expression is now work done of a continuous charge distribution, which is equal to epsilon naught over 2 we have integral of v e dot dA plus integral of, this is the surface integral now, e square into d tau. This is equation number 8. Now we have to simplify this equation now. So for that I will consider my initial equation, which is, this is the final expression. Here I will prove that this term is 0. It is approximately equal to 0. So we left only with this term. So I will prove that one now by using the theory. Let's go back to the equation number 4, which is work done, which is equal to 1 over 2 integral of rho v into d tau. Now suppose we have the charge which is assembled in this volume. And this volume I call it V prime. Now this volume includes the charge. Now I consider another volume outside this small volume V prime, I call it V. Now this bigger volume V also contains this charge, because charge is already inside this volume. Then this result will be the same if I consider this volume or this volume, because here in this region if I solve this integral, then it will be look like this: 1 over 2 integral of, it's from origin 0 to, let's say this volume has a radius r, capital R. It will be from 0 to r rho v d tau. Okay. Now it will be equal to 1 over 2. First from 0 to this small r, this is small r. Integral is from 0 to r rho v d tau, plus then from this small r to this one, then from small r to this r minus r rho v into d tau. Okay, like we have this small volume with radius r, this large volume with radius r. So if I consider this bigger volume, then this integral from 0 to r, this is from 0 to r, this capital R, can be divided into two terms. First is from 0 to r, and then from r to this point, and this point, this distance is r minus r. Now here in this region from r to r minus r, rho is 0. So again we have 1 over 2 integral from 0 to r rho v d tau. So it means that whether I consider this volume or this volume, the result will be the same. Now come to the first term, this term, which is this one, the surface integral of v e dot d. Consider this integral without potential. So we have this integral is e dot dA, and this basically gives us the flux according to Gauss law. Now this is the definition of flux. Electric field lines passing through a unit area is called flux. And for the flux, if I consider This is my charge distribution, okay? The charges are here. If I consider this volume, or this volume, or this volume, or this volume, the flux is always same on each surface, because if 10 lines are emerging from here, let's say how many? 4, 6, 8 lines emerging from this volume, then they are also passing from this volume. They will pass from this volume also. They will pass from this volume also. So they will pass from this volume also. Now the flux is constant and independent of volume outside the charge distribution, because equal number of lines, electric field line, like 8 lines started from here, that 8 line will pass through this volume, they will pass through this volume, so they will pass through this volume, so they will pass also from this volume. So it means that the flux is constant. So this term is constant. This term is constant everywhere, whether the volume is small or bigger. But the potential V, which is 1 over 4 pi epsilon naught Q over R, decreases as we move away from this charge distribution. The potential is maximum here. It goes decreasing if I move to this point. It decreases again if I come to this volume. It decreases again, and finally it will become 0 somewhere if I move away from this charge. So it means that this term is constant everywhere. This term is decreasing. So if I goes to a bigger volume with radius infinity, then this term automatically will become 0. So if it's become 0, then this whole integral will become 0. So it means that this term is integral of V into E dot dA is equal to 0 by considering overall space. By overall space, I means the space volume of all space, like the volume of the space around us. Then this term will become 0. If this term is become 0, the first term is gone. This is 0. So we left only with this term. So our final expression is, now I will write it here. The work done of a continuous charge distribution is epsilon naught over 2 integral of E square d tau, and this integral is include all space. So this is the final expression. Thank you.